It begins with a typical Ugandan morning routine. To boil water, you light a traditional metal stove by filling it with dark, rough pieces of charcoal. Later at school, a student sits down, scraping a pencil across the rough surface of a notebook to draw a diagram. Back home, there is friction in the morning routine. The water you pumped to wash your clothes reacts poorly with the soap, creating a sticky, useless white scum instead of a rich lather. The cooking fire, the dark trail on the page, and that frustrating soap scum all share a single, hidden chemical link. And while it helps cook breakfast, that exact same element is accumulating in the atmosphere, altering global rainfall and melting the Rwenzori ice caps. To protect our daily finances, our local forests, and the global climate, we have to understand the chemical rules governing this invisible shapeshifter, carbon. Carbon takes on completely different physical forms, known as allotropes, based entirely on how its individual atoms bond to one another. Take the diamond. It is the hardest known natural substance and completely unable to conduct a current of electricity. This animation shows us why. Every single carbon atom inside a diamond is locked into a rigid, three-dimensional framework by four thick structural bonds. Graphite is made of the exact same carbon atoms, yet it is soft, slippery, and an excellent conductor of electricity. In this model, the atoms form flat, two-dimensional hexagonal layers. Each atom forms just 3 bonds, leaving noticeable vertical gaps with weak forces. Press a pencil and these layers slide right off, sticking to your paper. Whether a material is hard enough to cut solid rock or soft enough to rub onto a notebook is entirely governed by its microscopic atomic architecture. Moving up from the atomic level, carbon interacts heavily with our local geography, especially in areas featuring thick deposits of white limestone rock. Rainwater absorbs carbon dioxide as it falls, becoming slightly acidic. As it soaks into the ground, it dissolves the limestone rock, creating a solution of soluble calcium hydrogen carbonate. This creates what chemists call hard water. When you pump this water from a borehole, the dissolved calcium compounds react chemically with your soap to form a wasteful white scum. The chemical workaround is adding washing soda. It forces the calcium out of the liquid as a solid precipitate, softening the water so you can actually get a lather. Beyond water management, Ugandans heavily rely on manipulating carbon-based materials, like wood, for daily energy generation. Through a process called destructive distillation, wood is heated in a traditional earth kiln with severely limited oxygen. This burns off the water and impurities, leaving behind mostly pure carbon. But there is a cost. While managed firewood is renewable, the rampant production of this charcoal destroys forests much faster than they can recover. Interacting with carbon at the human scale requires active chemical management, whether neutralizing disruptive ions in our water supply or carefully sourcing our fuels to prevent ecological collapse. At the atmospheric scale, carbon takes the form of carbon dioxide. It is an invisible gas that is denser than air and completely starves fires of oxygen. Because of that density, the gas sinks rapidly over open flames, making it the perfect chemical tool for extinguishing fires. High above us, it acts as a greenhouse gas. This diagram shows how naturally occurring carbon dioxide forms a thin thermal blanket, trapping just enough of the sun's bouncing heat to keep the Earth habitable. That human activities, primarily burning carbon-based fuels and cutting down carbon-storing forests, are releasing massive, unnatural excesses of CO2 back into the sky. That excess volume drastically thickens the atmospheric blanket, trapping far too much heat and accelerating global warming. This invisible change in atmospheric chemistry directly triggers the unpredictable rains and extreme droughts currently threatening local agriculture. Look once again at that morning routine. You can now see the invisible chemical realities underlying these everyday actions. You know the molecular layers sliding in the pencil, the dissolved calcium ions hiding in the wash basin, and the exact chemical reactions producing heat inside the stove. Understanding chemistry is a highly practical, active survival tool for modern life. Whether we are drilling through solid rock, fueling an economy, or trying to stabilize the climate, our future depends entirely on understanding and respecting the extreme dualities of the carbon atom.